Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back. We're going to go through an example manual that's mentioned in ASME Section 8 Division 1. It's referenced. It's called ASME PTB-4, and the particular one we're going to go through is the 2013 edition. That's the only one that I know about, and it's part 4. And the example we're going to go through is called Example E4.1.2, required wall thickness of a hemispherical head. So these are example problems intended to, with the whistle of the engineer, to have him start to really think about these problems. So they're set up in such a way that they kind of give you a really good example, but they don't quite explain it. So they make you kind of look through the book to really go through that. So I thought this would be a great video to sort of supplement that. So what's really interesting about the specs and is okay. We're following ASME boiler pressure vessel code section 8 division 1. And we're going to call this is abbreviation. We're going to call it, but little be known that there's a code case called 2695, and I've never used that, but apparently you can use part 4 if you want as which is division 2, which is called the alternative rules, and you can use part 4 calculations and substitute, but you have to still at the end of the day use the same allowables as division 1. And so I'd love to hear from someone who's actually gone ahead and used Division 2 rules as an alternative to Division 1. I'd like to hear what you have to say. But let's continue and dive into this quite interesting little problem here. Like before, we would be going into setting up our table like we always do. And so this is ASME Section 8 Division 1. It's always important to look at the edition. This is 2013, so the rules haven't changed too much, especially for this case. So we've got a material, 516 grade 70, so that's as per UG5. I've put a column here for you to sort of reference those in the tables. That's in addition to the sample problem. So we got a hemispherical head. Okay, we're going to talk about there's about 3 or 4 types of heads, but hemispherical head is one of the more common ones. And then we have at the bottom of the vessel, we have an inside diameter of 96 inches. We got a liquid head of 60 inches, a specific gravity of 0.85. We got a corrosion allowance. We got a category A and B weld joint category, which references from UW3. The weld joint type is UW13, which is very common in my part of the world, a type 1 weld, and I usually see without a backing strip, but there's backing strips as well. And the inspection 100% RT, post-weld heat treat. In this case, we're not doing that. And the joint efficiency, because of our inspections and the type of joint, our joint efficiency is 1. Our design pressure, it's getting pretty high. So this is why one can start considering using Division 2 rules, because the pressures are getting fairly high. So let's continue. Found in section 2, table 1A for section 8 division 1. And so here's an example of a table that we would typically use, and so you can see over here that it says section 8 division 1, and then basically we look at the temperature, which in this case is 150 degrees centigrade, and we determine that the allowable stress in our calculation should be 138 megapascals, which corresponds to the ASME A516 grade 70 plate material. To our preliminary calculations. So basically from that table that we showed you earlier, we've got 20,000 PSI or 138 megapascals. And we basically have to make an adjustment because our design pressure is equal to the specified pressure plus the hydraulic head, the static head, which is rho GH. So yeah, rho is a function of how dense the material is. And that was given in the previous table, gravity, that's given. And of course, H is for the head. So when we combine those together, as per UG1, we get an adjustment upwards to 1673.14. And that's quite critical for your design and your design pressure. And so let's continue with that. So we made that adjustment. Boiler Pressure Vessel Code, Section 8, Division 1, UG32E, has a couple of different different equations for different head configurations and shells. And so when we go to the library, Part E has to do with hemispherical heads. So they have two equations there that you can relate it to the calculate determine the thickness, or you can rearrange the equation and determine the pressure. Now we're going to continue on with example. That equation, there was a variable called L. So for the case of a hemispherical head, that is the inside spherical or what they call the crown radius. And with a hemispherical head, it's simpler. It's just because it's the same throughout. So basically that's how it's calculated. And typically we would use the corroded the corroded L. So you would have to take, increase that L of the new condition and add the corrosion allowance to get what you the final condition for that. So in comparison, you can see a hemispherical head, which is one of the most common you'll see. These are the two most common. There's other types, and perhaps in another video we can go through those geometries. But the other one is shown right over here, and you can see how much more complex it is. It's got two types of radiuses, and so it's quite interesting. And so the one that we're looking at in this example is the hemispherical head, which looks like this. So let's just go through this hemispherical head equation. I'm going to call this method 1 because method 2 is the division 2 version. And so again, we're going to take that inside spherical head, and then we're going to make the adjustment for the corrosion allowance. This is one way to do. You can use the radius, of course, and you make that adjustment as slightly larger. And then we do a couple of checks here. And this all goes back. You'll see this in the piping code as well, like B31.3. You have to make sure that the equations are following the thin walled stress theory or the thick walled. So this is an adjustment for that. So if you have something that's much greater than that, then you're okay. But if you have a very high thickness, then different rules apply and these equations don't work. The same here about the pressure and the stresses. So in this case, we went through the calculation. We just did an if then state calculation in Excel. We found out that both these equations are valid. So they made those pass. They both passed. So now we can go into equation UG32E into the calculation. As you can see there, we've come up with 2.03 inches. And if we adjust that with the corrosional allowance per UG16, we get slightly higher as expected, 2.155 or 55 millimeters. Now, there are some very important limitations with the calculations or restrictions. Maybe that's a better word. Uh, I want to bear in mind in the later editions, Appendix 32, there's requirements for local thinning. So if, say, for example, you're using a plate and it's been stretched, pulled, or for some reason it's thin, maybe due to bending, head forming, then there's restrictions on those. So there's very, very strict rules on those calculations. And you'll see a lot of that also more in Division 2 and fitness for service calculations. And next one is called a minimum thickness. There's a minimum thickness requirement for vessels, and so you should take a look at that for the code. And there's also some under tolerance restrictions for plate, so buying that plate. But that all feeds into the plate specifications as well. And so the other one, of course, is there's some notes about the corrosion allowance. Basically, it's saying you got to include those. Get this alternative method number 2, where you can use division 2 to do the calculation, but at the same time you have to go back and use the division 1 allowable stresses. So we're going to look at a little bit later towards the end of the presentation. We're going to compare them, but so we've done the math. Once again, I mean, they use slightly different terms, but D is basically the corroded diameter, and it's shown over here as 96.25 inches, and then basically you plug that into here. You can see this equation is as an exponent. It's a little bit more sophisticated equation. It's more intended for thicker walled vessels, and in this case we've got quite a high pressure, and so in this case, we're going to have to, post-well heat treat this equipment. It says earlier that there is none required, but it's required by code to do those. So we look at the corroded diameter, we plug that in, we get pressure, SE, and then we basically calculate the thickness to be 2.056 inches. And UG16 says we're at 2.181 inches, and we're done. The division 1 and 2 methods and to determine what's different. So we did division 1, we determined the thickness to be 55 millimeters, is 2.115 inches, and then we did the second method where we used the division 2 thickness calculations, but we have, in order to do that code case, we still have to follow the division 1 allowable stresses. And as you can see there's a minimum difference. For the hassle, is it worth doing it? You're not going to really gain much, millimeters. Where the advantage of division 2 is the allowable stresses. And then you still have to deal with if you're going to follow division 2, you're going to have to deal with things like we mentioned earlier, these tolerances. So that's probably why I've never seen Division 2 rules, but ASME allows that. But you need to also check with your local authority to confirm whether they'll actually allow that as well. And so, yeah, check with them. And if you're interested in doing that, and anyways, I hope you enjoyed this video. And if you send us a like and subscribe. And if you like these videos and want to continue to study the pressure vessel code examples, send me a quick email and I'll continue.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. and we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.